Ever get that like weird feeling when something, something you always expect to just be there at a certain price just suddenly
Yeah.
isn't?
Yeah, for sure.
I was thinking about it with coffee prices recently.
Yeah.
It's like they just go up and down all the time and you never really know why, right?
Yeah.
Is it like the weather in Brazil or something?
Right.
Or maybe it's like shipping costs, or maybe some, CEO somewhere made a decision and now, boom, my latte is more expensive. It's like we're all these tiny little pieces caught up in these like giant invisible systems.
100%. Yeah, we really are.
And that is actually what's so fascinating to me about this new kind of AI, something called large population models, LPMs.
LPMs, okay.
And you know how AI is already doing all these incredible things, right?
Yeah.
Like making those crazy realistic avatars, like the digital humans, or, figuring out what you're going to buy next on Amazon.
Uh-huh.
But with LPMs, it's different. This is about simulating entire societies.
Wow.
Millions of like digital people all interacting.
Interesting.
And you can use that to understand these huge, complex systems that we are all a part of.
So it's like instead of studying one tree, you're studying the whole forest and all the connections.
Exactly. You got it. It's like zooming out and getting that big picture view. And a lot of this is becoming possible now because of this platform called AgentTorch.
Okay,
It's open source, so anyone can use it, and it uses the power of GPUs, those things that make video games look amazing, to run these huge, massive simulations.
So that's how they're able to handle all the data and the complexity of these models.
Yeah, exactly. GPUs are like the workhorses here, crunching all those numbers.
Yeah.
But the big question is, why are we even doing this? What's the point of creating these digital nations? What can we learn from them that, we couldn't learn from just studying the real world? And that's what we're diving into today.
All right, a digital deep dive. I like it. We've got information from the AgentTorch GitHub page, a really interesting YouTube talk about LPMs, and some in-depth stuff from MIT Media Lab. They're like the pioneers in this whole area.
Cool.
So, why don't we start with, why do we even need to simulate millions of people? What's wrong with the AI and computer models we've been using up until now to try to understand these big, societal issues?
Okay, so are we talking about limitations, like why the old ways aren't good enough?
Yeah, exactly. What are those limitations?
Well, think about traffic in a big city, right?
Yeah.
You've got those models that try to predict the traffic flow.
Yeah.
Based on the time of day, maybe if there's an accident or something. But what happens when there's a big football game where they suddenly change the subway schedule?
Oh, yeah.
Those models, they kind of fall apart.
Right. They don't take those things into account.
Yeah, exactly. They struggle with all those interconnected factors and the way that our individual decisions, do I drive? Do I take the train? Do I just stay home and work? How all of that affects everything else.
It's like a ripple effect, right? One little change can mess up the whole system.
Exactly. In the YouTube talk we looked at, they had this really good example.
Okay.
With the bird flu.
Okay.
Right? It wasn't just about sick birds. It was a whole chain reaction.
Yeah.
So you had infected birds migrating, going across borders.
Right.
Leading to outbreaks on poultry farms.
Yeah.
Which made the price of, eggs and chicken go way up.
Makes sense. Supply and demand.
Yeah. And then it impacted the dairy industry because they had to cull the birds to, stop the spread. And then there were even concerns about, could this jump to humans?
Right. It could become a pandemic.
Yeah.
It's almost like, a domino effect, but with millions of dominoes all falling in different directions.
Yeah, and you don't know which way they're going to fall.
It's chaos.
Right, exactly. So with so many individual birds and farms and consumers and decisions, traditional AI just can't really grasp the whole picture.
Yeah, too much going on.
Too much. In the MIT document, they talk about this thing they call the scale versus detail dilemma.
Okay, what is that?
So basically, with the old models, you had to choose between a really detailed model of just a few individuals, really understanding their behavior, or tracking millions of simplified agents, but not really knowing much about them individually.
Right. So it was either like a super close-up of a few people or a blurry satellite image of the whole world, but you couldn't really have both at the same time.
Exactly. It was a trade-off.
So how does AgentTorch deal with this? How do they get past this, scale versus detail problem?
Well, it's all about the architecture, how it's designed.
Okay.
It's built for both massive scale and what they call composition.
Composition.
Yeah. And on GitHub, they actually talk about how their models can simulate populations the size of entire countries,
Yeah.
and they do it quickly.
A whole country. Wow. That's pretty amazing. How is that even possible? How do they make it that fast?
So in the technical documents, they go into these concepts like composable interactions
Right.
and tensorized execution. It's a mouthful.
It is.
But basically, they figured out a way to like break down those complex interactions between millions of simulated people into smaller reusable pieces.
Okay.
And then they use the GPUs, the power of those GPUs, to compute all those interactions at the same time. So it becomes much faster.
So it's like instead of doing things one by one, they're doing millions of calculations all at once. Like it's like having a giant team working on the problem.
Exactly. A massive parallel processing team. And then there's this other clever thing they do.
Yeah.
It's called agent archetypes.
Oh, okay. What are those?
Well, instead of trying to model every single person is completely unique, with all their little quirks and habits,
All right.
they group people into these like categories based on shared characteristics. Like think about it like in a video game.
Okay.
You've got different types of characters, right?
Uh-huh.
Like the warrior, the mage, the healer. They have similar skills and abilities.
Right.
It's kind of like that.
So it's like a shortcut to make the simulations more efficient.
Exactly. But they're not sacrificing too much detail. Like if you're modeling how a disease spreads, you might have archetypes for, young children, working adults, and seniors.
Right, because those groups behave differently.
Yeah, they socialize differently, they have different health risks, and so on.
Yeah, that makes sense.
Or in an economic model, you might have archetypes based on income or profession, because that affects how people spend their money.
Right, their financial decisions. So it's about capturing those broad differences without having to, model every single person in excruciating detail.
You got it. Efficiency and accuracy.
I see. Now, the technical stuff also mentioned this language called Flame.
Flame.
Yeah. Composable domain-specific language. What's so special about this language?
It's really cool, actually. It's like a universal translator for models.
Okay.
So imagine you want to understand how, like, a new economic policy might affect the spread of a disease.
Right.
With Flame, you can take a model of disease transmission, a model of economic activity, and even a model of how people move around.
Okay.
And you can combine them all into one big simulation.
So you could see how, unemployment rates might affect whether people go out and how that impacts the spread of the virus.
Exactly. You can see those complex real-world connections, how everything is intertwined.
That's really powerful. But, you have these massive simulations running. How do you actually connect them to what's happening in the real world?
That's a challenge, right?
Yeah.
We've got all this data, like how many people go to restaurants, how many are getting sick, traffic patterns, what people are searching for online.
Yeah, tons of data.
But it's hard to, link all that real-world data to these complex simulations.
Right, and understand what it all means.
Yeah, and how it can help us make better decisions.
Exactly. The MIT overview calls this the puzzle piece challenge.
Puzzle piece challenge.
Yeah, it's like having all these pieces of a puzzle but not knowing how they fit together.
I get it.
So how does AgentTorch approach this puzzle? How do they connect the simulation to reality?
This is where it gets really interesting. They make their simulations differentiable.
Differentiable? What does that even mean?
It sounds kind of technical, but bear with me.
Okay.
Think of it like this. It lets the model learn directly from real-world data,
Okay.
like stuff from hospitals, transportation systems, and so on.
Right.
And then it can adjust itself to better reflect what's actually happening.
So it's like a self-correcting simulation.
Yeah, exactly. It's constantly learning and updating itself.
Wow.
The technical documents, they talk about something called differentiable agent-based epidemiology.
Okay.
And that uses some fancy math to, fine-tune the model based on what's really going on.
So it becomes more and more accurate over time.
Yeah, and more useful for predicting real-world outcomes.
The MIT paper had this example with, a restaurant owner named Maya.
Oh, yeah.
And it's like if her restaurant suddenly has fewer customers, an LPM could help her figure out why.
Right, is it because of a disease outbreak?
Mm-hmm.
Or maybe some new government restrictions?
Or maybe people are just, staying home because they're worried about the economy.
Right, a drop in consumer confidence.
And then the really cool part is it could also predict how different things she might do, like offering discounts or making her restaurant safer, how those things might affect her business and public health.
So it's not just about understanding the problem. It's about finding solutions.
Exactly. It's like having a crystal ball that can show you the potential consequences of your actions.
And a very data-driven crystal ball.
Exactly. Now, even with these, super accurate simulations, there's still this problem that the agents in these simulations, they're not real people.
Right? They're just lines of code.
Yeah. They don't have all the complexities of human behavior. They don't have emotions. They don't change their minds unexpectedly.
Yeah, they're not going to suddenly decide to, like, quit their job and move to Bali.
Exactly. The MIT people call this the simulation versus reality gap.
The gap between the digital world and the real world.
Yeah. So how do we close that gap? How do we make these simulations more realistic?
Well, AgentTorch has this really interesting idea.
Okay, tell me.
What if we could use our own devices, like our smartphones, as part of the simulation?
Whoa, hold on. So, like, my phone would become a little digital person.
In a way, yeah. It's about creating these decentralized simulations.
Okay.
Instead of having everything happen on one big computer, the simulation could run across a network of individual devices.
Okay, but like, what about privacy? What if people don't want their data being used in some giant simulation?
That's a good question. And that's why they're building in all sorts of privacy-preserving technologies.
Okay.
Things like secure multi-party computation.
Right.
It's a way of doing calculations without revealing the underlying data.
So my phone could be part of a traffic simulation without anyone actually knowing where I am.
Exactly. And the perspective document talks about these immunity networks.
Immunity networks.
Yeah, it's kind of like our devices could talk to each other anonymously to create, like, dynamic safety zones.
Okay.
Maybe suggesting less crowded routes or letting us know about potential risks without giving away our personal information.
So like crowdsourced safety information, but private.
Exactly. It's
Yep.
all about finding that balance between using data for good and protecting people's privacy.
It's a tough balance for sure. But all this sounds very theoretical. Are these LPMs actually being used to solve real problems right now?
They are. Actually, both the GitHub and MIT materials have some pretty cool examples.
Really?
Yeah. They've been used to help figure out the best way to distribute vaccines,
Wow.
to make sure they reach the people who need them most.
Okay.
And they're being used to track global supply chains.
Oh, that's so important right now with all the supply chain issues.
Yeah. And they even helped New Zealand deal with measles outbreak.
That's amazing. So they're already having a real impact. And the GitHub mentioned something about like reinventing the census using continuous simulation.
Yeah, that's the long-term vision.
That's a big goal.
It is. And the idea is to have a more up-to-date understanding of the population because, the traditional census only happens every 10 years in a lot of places.
Yeah, it's very slow.
Right. And then there's this whole concept of protocol-centric intelligence that they talk about in the perspective document.
Okay, what is that?
Well, it's like a roadmap for how AI agents could evolve and, coordinate things in the world.
Okay.
They describe these 5 levels
5 levels of what?
of, like, how AI can become more integrated into our lives.
Okay, break it down for me.
So the first level is about individual awareness,
Okay.
like your smartwatch telling you to get more sleep because you've been, sitting around all day.
Right.
The second level is about local interactions, like between a small group of people,
Okay.
like your phone adjusting your ETA because other drivers are reporting traffic jams.
Right. Real-time updates.
Exactly. Level 3 is about social coordination within larger networks,
Okay.
like a community energy grid that automatically balances supply and demand.
So it's getting more complex.
Yeah. And then level 4 is where LPMs really come in.
Okay.
This is about global orchestration.
Global orchestration. That sounds intense.
It is. It's about coordinating things on a massive scale.
Okay. Give me an example.
Like, imagine a farmer using an AI agent that helps them decide when to plant and sell their crops based on global weather patterns, market prices, and, shipping logistics.
So it's like a super-powered financial advisor for farmers?
Yeah, something like that. Or a city planner using LPMs to see how different infrastructure projects would affect traffic and energy use across the whole city.
So it's about making smarter decisions that benefit everyone.
Exactly. And then the 5th level, the most ambitious one, is called physical integration.
Physical integration.
Yeah, this is about like closing the loop between the digital world and the physical world,
Okay.
creating these living feedback loops. Like, imagine a network of self-driving cars coordinating their movements to optimize traffic flow in a city,
Wow.
or smart buildings adjusting their energy use based on weather forecasts and how many people are inside.
That's pretty mind-blowing. We're talking about AI that can actually shape our physical environment.
It's a powerful idea.
Yeah.
And it's why it's so important to think about the implications, you know.
For sure. This is some serious future stuff. So, to recap, large population models are a totally new way to understand and address those big, complex problems that we face as a society.
Yeah.
They can handle massive amounts of data, they can learn from the real world, and they might even be able to bridge the gap between the digital and physical worlds, all while keeping our data private.
And I think what's really exciting is that it's not just about individual AI anymore. It's about designing these intelligent protocols that can help us coordinate and work together on a much larger scale.
That's a great way to put it. It's like we're writing the rules for a future where AI helps us make better decisions as a collective.
Exactly.
And for anyone who wants to dig deeper into all this, check out the AgentTorch GitHub page. It's got all the technical details.
Yeah, it's a great resource.
And the MIT Media Lab has a whole website dedicated to large population models research.
Definitely worth checking out.
It really feels like we're on the cusp of something big here. Like, we might finally be able to understand these complex systems that shape our world, and maybe, just maybe, we can use that knowledge to create a better future.
I hope so. It's an exciting time to be alive.
It really is.
Yeah.
All right, well, that's it for our deep dive today.
Thanks for having me.
It's been a pleasure.
Likewise.
And we'll catch you next time for another deep dive into the world of AI.
Sounds good.
Until then, keep learning, keep exploring, and keep asking those big questions.
Absolutely.
Take care.
Bye.